comment or question about our previous lectures. And also, if you can confirm that you can hear me, that would be appreciated, because it's never clear to me if things are working properly. So this is the part that we are going to do today. So just to be clear, this is going to be the exercise part on the lectures number 11 and 12. Yep. Okay. Anything special you would like to see about these exercises, or, you know, anything else we saw? Otherwise, I start doing them in the order I suggested you to have a look to them. So say we can start by something like this. I take a matrix 4 by 4, and I ask you to compute the determinant of this matrix. As you can tell, it has a nice shape, but let's see. So let's start by computing the determinant of this one. So we'd like to know what is the determinant of matrix A. And you can compute it as you prefer. And then we'll play with the question of taking a real number lambda. So this is the first task. And then the second task will be to try and see what is the determinant of lambda A. But first, of course, we should find the determinant of A. So we have a suggestion of Seyedi, which it's not clear to me. Do you suggest it is 4 or -4? -4. Okay, so let's say we compute this determinant together, also because it is 4 by 4, a little bit larger than the usual. You cannot use Starus rule here, so you need to use our recursive definition. And it's possible to start by any row you want to perform this computation. This we know by Laplace theorem. But let's say we start by the first row. So I start computing the determinant of A. And what I'm doing is looking at the first row of this matrix. And then you see you will have to do what? To multiply 1 by the determinant of the matrix, which we call A11, and then -2 times the determinant of the matrix that we call A12. Right? This is the first step. And then, of course, you can use Laplace and use row 3 or row 4 because that's smarter, because they are smaller. Yeah, that's perfectly fine. But I'd like just to make a small remark here. So now let's see what are these matrices. So this is the determinant of a 3 by 3 matrix, which is 3, 4. Well, not exactly. It is 4, 0, 0, and then we have 0, 0, 1, and then we have 0, 1, 0. And then it is -2. The determinant of A22, so it is the matrix you obtain by deleting the first row and the second column, right? No, now I made it too large, sorry. So it is 3, and then there is a 0 here, 0 there, 0, 1, 1, 1, 0. And what you do if you do one step further again, developing with respect to the first row, you will get 1 times 4, and then you get the determinant of this matrix here. And you get -2, which is 2 times 3 times the determinant of this matrix here. And if you play just a little bit, you will see that you get 1 times 4 minus 2 times 3 times the determinant of this matrix here. And this determinant here is not probably a surprise. This is the determinant of the matrix 1, 2, 3, 4. Right? So the conclusion is that if A is like this, so if A is like this, let's put it here, then what we get is that the determinant of A is the determinant of these 2 by 2 times the determinant of these other 2 by 2. Okay? So what we get at this point is determinant of, call it B, here it is, times the determinant of C. And this is a typical situation of these block matrices. So let's make a quick note. A block matrix is a matrix A in which you have a lot of square matrices on each staying on the diagonal and a bunch of 0 outside. So this is an n times n matrix. Each of these AI is square. And lies on the diagonal. Then the determinant of matrix A is equal to the determinant of A1 times the determinant of AR. So square on the diagonal. So this is a generalization of what we know about diagonal matrices in which the determinant is the product of the diagonal elements, right? So this is just to say that if you want to compute this determinant, you just need to look at the determinant of the smaller matrices because you have the block structure. Okay, and that makes life, you know, much easier. You can do computation more quickly by using the structure of your matrix. And in this case, we obtain that the determinant of matrix A is equal to the determinant of matrix B, which is minus 2, times the determinant of matrix C, which is minus 1. And so this is 2, right? It is minus 6 plus 4, minus 2 times minus 1. So it's going to be 2. Okay, good. Now we want to make the same computation for the matrix lambda A. But you see, the matrix lambda A is not probably a mystery, right? It's not mysterious what the matrix lambda A is going to be. You multiply each entry by the number lambda. And so when we think of this block structure, so having matrix, we call it B here, so this is lambda B, and we call it C, so this is lambda C. So what I'll get is that the determinant of lambda A is the determinant of lambda B times the determinant of lambda C, which in our case we see is lambda times minus 2, lambda times minus 1. So the result is 2 lambda squared. So what is the conclusion here is that the determinant of lambda times A is 2 lambda squared, where the determinant of A was 2. So you multiply by these lambda squared, no matter what lambda is. So there are a couple of questions in the chat. Let me see. So Erfanfar, can we use this one if the second determinant on the other side of the diagonal? Not completely clear to me, Erfanfar, what you mean. So you mean putting matrices here? No, that's not a block matrix anymore, no. These Jean Herrera, yes, they are from 11 and 12. Yeah, yeah. So it's the exercise sheet number 6. Shouldn't it be lambda 4? Yes, it is, because it is lambda square here, lambda square there. So let's put this in red because I miswrote. Yep, thank you. Who's there? Pascal Riaki and Davide Putorti. Yep, you are correct. So I was talking too fast. This is 4, of course, because you multiply 2 by 2. Yeah, thank you. Okay, so this is what you get in this special example. And actually, this is not just because it is a blocks matrix, because these are not block matrices, but you multiply the result by lambda square in both cases. And that's because they are 2 by 2 matrices. So what is true, and let's make a note, is that when you compute the determinant, if you have your matrix A n times n, when you compute the determinant of lambda times A, what you get is lambda n determinant of A. And the reason why this is true is coming from Binet theorem, because lambda A, if you think about it, is just the diagonal matrix with lambda on the diagonal times A, right? And so when you apply Binet theorem, you will get the determinant of lambda A is the determinant of this diagonal matrix with all lambda on the diagonal times the determinant of A, and this is lambda to power n determinant of A. So this is because of Binet theorem. It's helping you because you can factor your matrix lambda A. You can describe your matrix lambda A as a product of these two matrices, a diagonal matrix and then just your matrix A. And so you get the result you want. Okay? Good. Then, if you want to see 6.4 is what we did with the elementary matrices. So we don't say much about that one, but we can speak about 6.5 a little bit. So we can try this situation, 6.5. So for example, we can say, well, I'd like to compute the determinant of a matrix like this. Say, as before, we make it 4 by 4. So it is a block matrix, just to make our life simpler. And we want it to be skew symmetric. So I'd like you to tell me what I have to put in these, say, green spots to make it skew symmetric. You can choose, make your choice. What do you want it to be? So what do you want it to be, for example, here and there in the first block? What do you want to add there? Just give me numbers so we can play with them a little bit. So maybe who's the last person who wrote in the chat? Gabriele Tarico. Well, Ash Bairagi suggests 1. Okay, so I put 1 here. And then what should I put here? Ash Bairagi. -1. Okay, that's good. And then there is Rebecca Iudicello, just because she suggests 3. And probably we all agree should be -3. Or if you want, you can also revert them, right? So we compute this determinant, and I know is going to be the determinant of the two blocks. And so what I get is number 1 times number 9. So I got 9. So nothing special happens here, right? Because this is 4 by 4. And if you look in the exercise, it was speaking about odd size. Okay, so let's try to make a skew-symmetric matrix of odd size. Just to keep playing in this way, I take one of your suggestions. So again, make it a block matrix, but now a little bit simpler for us to play with. So something like this. Well, no, let me write it properly. So something like this. Let's do 3 by 3 because we want odd. So I know skew symmetric, I have to put zeros on the diagonal. And then I can put what I prefer outside the diagonal. So something like this. Okay, and then we can go and compute this determinant. So let's call this B so we don't get confused. So I will now compute the determinant of B. And, you know, if we want, we can play a little bit with elementary operation. If you want to get more zeros to show up, for example, in a row or in a column, you can play that kind of game. So, for example, I can decide to make a 0 to appear here. Okay, so if I want, I can say that this is the determinant of a matrix I obtained from the previous one, 0, 1, 2, minus 1, 0, minus 1, by changing row 3 into row 3, and then I can do minus 2, row 2, if I want. So that if I do that, I get a 0 to show up here. Maybe I like that. So I do this, then I still have a 1 there, and then I will have a 2 in this position. Okay, and now what I can do, well, remember, we just said that the determinant of a matrix and of its transpose, they are the same. So I can compute the determinant with respect to the first column. So this is the elementary row operation I use here to obtain these matrix C, and C and B are row equivalent. And then I can compute the determinant of C transpose, and it's going to be to this one, right? This is the previous exercise, what we said during the lecture also. So I compute the determinant with respect to the first column. So first column. Since the determinant of a matrix and of its transpose are the same. And so I can just say it is depending on this minus 1. So I have to take minus 1 to power 1 plus 2 because it is row 2, column 1. I multiply by minus 1, and then I multiply by the determinant of what I get by deleting column 1, row 2. And so I get 1, 2, 1, 2, and so I get number 0. Okay? Also, as some of you very smartly note, these two rows are equal. And so, of course, the determinant must be 0. Perfect. So we obtain a 0 determinant. And the fact is that whatever you do, okay, whatever you do with your skew-symmetric matrix, it is always going to be like that, okay? And what is the trick here? What is the note we want to make? Because we want to remember this, is that if I have n skew-symmetric matrix, so Q symmetric, n times n odd, then the determinant of A is always going to be equal 0. And why is this the case? So why is this true, that the determinant is always equal 0? Well, this is because skew symmetric means that the matrix, if you transpose it, is equal to its opposite. Okay? I finish this and then I go reading in the chat, okay? So just follow me for a second. So the determinant of the transpose must be equal to the determinant of the opposite. And from what we learned, the determinant of the transpose is equal to the determinant of the original matrix, while the determinant of a matrix times a number is that number to the size times the original determinant. And as we have an odd size here, it means that what we get is minus the determinant of A. Okay, so this means that whenever you have a skew symmetric matrix of odd size, 1, 3, 5, and so on, you will get to the value of the determinant, which must be 0, because we obtain that the determinant of A is equal to the opposite of the determinant of A, and so it is equal 0, right? The only number which is the opposite of itself is 0. Okay, good. So now let me see in the chat for a second. Camilla Tetti says about matrix C, I think. Well, of course, it's going to be the same because you remember two matrices which are row equivalent are such that one of them has determinant 0, if and only if the other one has determinant 0. So being able to prove that you find the matrix equivalent, row equivalent to be of 0 determinant, it is enough to say that the original matrix had a 0 determinant. Then there is Seyedi asking about the note. So the note is what we just explained, right? So let me know if you have any further doubts, or if it is okay for you to say that the determinant is 0. Well, the exercise sheet, I can try to do that. Yes, should not be a problem. So let's see. Just a second. That should be easily done. But I prefer that you always download all of them before, because otherwise it's a lot of extra work we have to do during the lecture and make it a little bit more difficult to proceed. But maybe now is a good time so you can have time to think about any question. So this is this one here. But I encourage you to download them before. Okay. Okay, so let's see. What we do next is to speak so this is the note we want to make, and the exercise who's asking Amos Lanzuis is just a pretext to show that if you have a skew symmetric matrix which is even size, nothing special happens. But if it is of odd size, then you get zero determinant, and that's not just a chance, it's something that happens consistently over and over again. Okay? So this is what we want to mention now. Okay, so let's say something more about about subset and subspaces. So I just copy the text here. So if you don't have the latest version, everything should be fine. So let's see, for example, this one. So we have this V, say X, Y, Z, and say X plus Y equal Z plus 1 equals 0. And let's say we want to know, is V a subspace of R2 or not? Let's see. Let's see what we can say about this. Pascal Ariaki asked about 6.6. Yes, we can have a look to that too. Yeah, just let's go for a subspace for a while, and then we have a look to that too. So now just look at this one, the subspace one, and let me know what you think. Is it subspace, yes or no? And then we can decide if we have a good argument for saying yes or no. So Federico Moro says no, it is not. And why it is not? So do we have an easy way to convince us that it is not? Yeah, so just a quick note here. You see, it is written in one line, but what does it mean is simply that you want at the same time X plus Y to be equal Z plus 1 and Z plus 1 to be equal 0. Or equivalently, if you want that X plus 1 Y, sorry, is 0 and Z plus 1 is 0. So these are equivalent system of equations. Should not be a surprise, right? So actually this V is a solution set of a linear system. So why is it not a subspace? Since it is a solution set of a linear system of equations, why is it not a subspace? Isn't that enough to be the solution set of a linear system of equations? In what Federico Morro and, oh, sorry, it is R3. Thank you for letting me know. It is a 3, not a 2, because we have X, Y, and Z. Thank you. Yes, so you're saying a lot of things. And what is the point? The point is that this system is not homogeneous, right? Not homogeneous. And why it is not homogeneous? Well, because there is a 1 here, right? So I did not take all the known terms to the right. Okay, so it's a solution set of a linear system of a, say, non-homogeneous. And so this is not a subspace, no. And the reason for saying no is that, as many of you said, the 0 of R3 does not belong to V. And so the necessary condition, it is not satisfied. And so we say it is not a subspace. Okay, good. this is why we say no way it is going to be a subspace, because the zero element is not there. Good. Before forgetting, who was there? Pascal Riaki asked a question about an exercise, so it's probably a good idea to have a look. So it is the 6.6, which I write it here. So it says that if you have a matrix A, which is A times B, then you have a matrix B, which is B times A. And if we say that A is larger than B, then one of the two products, so B times A, sorry, it is A times B, which is a matrix A times A, right? Well, this matrix here, with this condition, has the property that its determinant, it is 0. Let's see in a couple of examples maybe what this is going to mean. So very simply, let's say that A is a 1, 0, 1. So it is a 3 by 1 matrix. So B is going to be a 1 times 3 matrix. So whatever you want, 1, 2, 3. And then we want to say something about A times B. So what is A times B? It is a 3 times 3 matrix, which we can describe well, right? If you remember, there is a nice way to describe it, or you can compute. But what can we say about the columns, for example, of this matrix here? They are easily determined, right? Because they are just all multiples of A. So they are something 1, 0, 0, because I use this number here. Then it's going to be 2, 0, 2, because I use this number here. And it's going to be 3, 0, 3, because I use this number here. And, well, not a big doubt that the determinant of AB is 0 here, since we have a 0 row, right? So having the 0 row here makes it pretty obvious that the determinant is 0. So everything comes from this 0 there. But what if we change it a little bit? So let's change it. So let's say we have the same scheme, the same situation, but we change it a little bit. And precisely, I change this in another number, say 2. Okay, so what is going to be AB this time? Well, also remember that this is also easy to describe as rows, because all the rows are multiple of 1 to 3. In particular, you get 1, 2, 3, 2, 4, 6, 1, 2, 3. And again, the determinant of this matrix is 0. Well, because I have 2 equal rows. But even more, right, is not just because I have 2 equal rows, but even the first 2, you see, they are multiple, one of the other. And so when you compute this, you get 0 determinant, because after a linear combination, you can reduce this to have zeros. So let's see how these could work in general. Okay, so what is the general situation? So in general, what will happen? Well, in general, I will have my matrices A and B. So matrix A is A times B. and matrix B we said is B times A. And I want to have a look at the product AB, which is going to be A times A. And we know that A is more than B. Okay, like in this example, A was 3 and B was 1. Okay, so what I can say about matrices? Well, matrix B will have B rows, row 1 and row B. Okay? When I multiply A times B, what I will get here? Well, I will get the A rows of matrix AB. So let's say this is going to be, let's call it M1. Then there will be MA, but then, sorry, there will be MB. And I keep going till I get MA. So look, what is the connection between these two matrices? The fact is that the rows of AB, so the rows, so the A rows of AB are a linear combination of the B less than A rows of B. And then we ask, is the set of the rows of B linearly independent? Can you answer this question? Is this set linearly independent? Are the rows of B linearly independent? Jean Herrera says, no, they are not. And this is what I try to suggest you by showing you this. But why are they not linearly independent? Well, because row MA, for example, row MA is going to be a linear combination of these B rows. So it's going to be a linear combination of the previous rows. So the fact is that the answer here is no. And there exist zeros. Well, actually there exists a zero, an elementary row operation, such that if I multiply these by the matrix AB, I get a 0 row. I get a 0 row. This is the idea we want to implement here, right? So the rows of AB are a linear combination of the rows of B. And so we get that there exists an elementary row operation such that when you multiply like this, you get a 0 row. And getting a 0 row, it means that the determinant is 0. Because the determinant of a matrix linearly row equivalent to AB has a 0 row, so is 0. The rows of B are not linearly independent. We cannot say that. But what we can say is that the rows of AB for sure are not, because they come as linear combination of the rows of matrix B. So what is the idea? The idea is that you can look at this matrix, you will reduce it, and you will get at most B markers. So when you use these rows to produce a larger number of rows, they cannot all be containing a marker. There will be rows with a zero. Sorry, without markers. And row without the markers are rows you can make zero with elementary row operations. So the idea is that when you multiply two matrices, what happens is that if they have these AB and BA size and you obtain the largest possible matrix, then that one is not going to be invertible. That one will have zero determinant. And it's going to be clear if you think about the row space. So I just write it for you. So the row space of AB is inside maybe equal to the row space of B, but cannot be larger. It cannot be larger. And so since B is smaller than A, this is why the rows of AB cannot be linearly independent. So what I suggest now we do is to go and see something about elementary, about row space and column space of matrices, so that we practice a little bit about those, okay? So let's try to do this. Before doing that, let's speak about one more of these subsets. So X, Y, Z in R3, such that X equal Y equals Z. And we ask if is V a subspace of R3 or not. So is V a subspace of R3 or is it not? Okay, so for example, Daniel Calviero says, yes, it is a linear span. But I'd like you to say more about that. Sofia Carnau say yes, but she does not say why. So I'd like to see more. Why do you say it is a linear span, for example? Or why do you say, Walter Ghirotti, yes? Can you give an explanation? The only explanation I see, the one by Daniele Calviero, I don't really understand very well. So let's see if you can explain me. So 0 belongs to V, it is a necessary condition, but it's not sufficient, right? Walter Ghirotti, be careful. So what do we need to do to be sure that it is a subspace? We need to check S1 and S2. So one possible way of doing this is check S1 and S2, but be careful, checking that 0 is inside is not a sufficient condition, is necessary. So you just need to check S1 and S2. And the best way of doing this is to say, well, V is the set of elements of the shape X, X, X in R3. So for example, if you want to check S1, you need to take V1 and V2 inside V, and you need to prove that V1 plus V2 is inside V. So if you want to check this one, you need to prove this. And how is V1 looking like? Can you tell me how is V1, the general V1 looking like? So what is this shape? Well, that's a special V1, right? Yes, this is more like that. It is a triple of equal numbers. Similarly for V2. So when you compute V1 plus V2, you will get again a triple of equal number, x1 plus x2, x1 plus x2, x1 plus x2. And this is again, so it is clear that V1 plus V2 belongs to V because it's made by 3 equal numbers, right? So this is how you can see that. Okay, and similarly, you go and prove S2, okay? But there is also another way of doing that, that probably is what some of you suggested at the beginning. Since V has the previous shape, it is the linear span of 1, 1, 1, because all multiple elements are multiple of this, and so it is a subspace because it is a linear span, right? And there is also a third way of thinking about this, because V is also a kernel. Can you tell me what matrix is giving me V as a kernel? Do you see it? No, Sophia Carnot, because the kernel of the identity matrix, if you think about it, since it is invertible, it is the zero space. No, so it's not the kernel of the identity matrix. I suggest that you go back and see that this is a linear system of equations, right? So write it down. So this x equal y equals z. What is the matrix associated to this system? Let's see if you have some nice idea. Yes, so that will look better because it is x equal y, and if you want, y equals z. And so in matrix form, this system is exactly what you wrote, 1, 1, 0, 0, sorry, it is 1, minus 1, 0, 1, minus 1, times x, y, z. So it is a 2 times 3 matrix. So this is matrix A, 2 times 3, but the kernel is inside R3. So that's perfectly fine. We don't need it to be 3 by 3, right? For the kernel. Amos Lanzu is, yes, basically, when you say it is a kernel, you're saying it's the solution set of an homogeneous system. Yeah, so it is exactly the same thing. So you see, you can answer this question in these 3 different ways. You check the properties, you see it is a linear span, you see it is a solution set of a homogeneous linear system of equations, which means it is a kernel, and so you get the answer you want. That is, you get the fact that it is a subspace. Okay, so if this is okay, we can probably move to something slightly different and speak about row space, column space, and the like. So we practice a little bit these notions. So I write this. So compute the column space of A, the row space of A, and the kernel of A for some matrices. And let's say we start with one very specific matrix, these 1, 2, 3, 4, 5, and 6. Okay, so let's see what are these three subspaces: column space, row space, kernel. Also try to decide first subspaces of what, and then once you decide that, you go and compute them. So let me connect the charger before it's too late. Okay, so let's have a look to what you are suggesting in the chat. So this matrix is 3 times 2. So I just do one step at a time. So column A is made by the columns. So since the columns are vectors of length 3, this is inside R3, 1. Okay? And you can, in some sense, say this is not much different from R3. I agree, but if you want to write them as columns, well, this is probably best. And this is the linear span of these 2 vectors of length 3. Okay, here it is. In the same way, if I want to speak about the row space of A, so looking, for example, Jean Herrera, you did it correctly, but just keep in mind that if you say R3, you're in some sense decided that you don't care about rows and columns anymore. Not a mistake, not a problem, but depends on the application you have in mind, okay? So the row space is given by the 3 rows, right? So it is inside R1, 2, which you can say, well, it is not much different from R2. And I agree, it's not much different, but they are not equal. Okay, they can be identified, right? And so you say, well, this is generated by 3 rows, 1, 2, 3, 4, 5, 6. And probably, you will start suspecting that since there is a 3 here, 2 is probably what I need. But since there is a 2 here, these 3 probably are not all necessary. And actually, this is equal to the linear span of 1, 2, 3, 4. And the reason why this is true is that if you take the matrix A, 1, 2, 3, 4, 5, 6, this is row equivalent to this matrix here. So you can apply elementary row operation in such a way you cancel the last row. Try, you will see. And this is why you only need 2 of them here, because this matrix has rank 2, not 3, since it only has 2 columns, cannot have rank 3, right? And then we finish with the kernel of A, which is the one you don't read directly from the matrix. So just looking at the matrix, I cannot say what the kernel is. I can say where it is living, because it is living in R2. But if I want to find the kernel, then I have to work a little bit more, because I have to solve AX equal 0. Okay? So I have to solve AX equals 0. And now I'd like to see what you think the kernel is. So Thea Armouche has a suggestion, 0110. How can we say if the suggestion is sensible or not? Well, what you can do is take an element of the kernel, right? Call it V. Then you compute AV. And what should you get if V is an element of the kernel? What do you say? You should get 0. Exactly. And you know that if you take 0, 1, or 1, 0, you don't get 0, right? So the kernel is not that one, right? So what is the kernel? Can you compute it for me? Oh, Tearmush, you're right. The row space of A is R2. Yes, because, so you did something smart. You said, well, I keep row reducing and I get 1, 0, 0, 1, 0, 0. So this means that the row space of A, so this green part here, means that the row space of A is actually R2, the linear span of 1, 0, 0, 1. Yeah, you're correct, because you can keep this row reduction step. That's true. And when you apply elementary row operations, you don't change the row space. Yeah, exactly. So we can make it into a note. It's probably a nice idea, but it is written in the notes. If you have two matrices which are row equivalent, then they have the same row space. And we also know they have the same kernel because the linear system of equations are equivalent, right? And so this probably should help you to compute the kernel of A just by looking at the green matrix. So what is the kernel of A then by looking at the green matrix? Exactly, you see, that is a rank 2 matrix. So this matrix has rank 2. And so by Rouchet-Capelli theorem, the system of equation has infinite to the 2 minus 2 solution. So it has only one solution. And so the only solution is the trivial solution. And so the kernel is just the null space. So it means that the kernel of A is just the null space, the 0 of R2. Okay, so this is the situation here, right? It's not square, and so I don't see exactly, so we're saying something. Well, upper triangular, lower triangular, yes, that you can apply. But I don't see why you worry about being square, Jean Herrera. Why are you worrying about that? Oh, because it's not square. Oh, I see what you mean. Oh, I see what you mean. Yeah. Well, that's a matter of definition, right? So upper triangular, lower triangular means that the possibly non-zero elements are above and below the diagonal. If you want, you can give an extension to even non-square matrices. But I agree with you. I would not call this green matrix triangular because it's not square. But if in some application you need to give it a name, it is very close to below upper triangular, right? Because it has this bunch of zero below the diagonal. The fact is that if you don't have a square matrix, the notion of diagonal is a little bit awkward in some sense. Okay, so any further question about these row space, column space, and so on? If not, we will just do the next part of this exercise. So let me go back so you see what the point is. We take exactly the same thing, but we transpose A, right? So we have the same questions, but not for this matrix here, but for the matrix which is the transpose of this one. So 1, 3, 5, and 2, 4, 6. So it is the transpose of the previous one. And so it is not 3 times 2 anymore, of course. So the transpose of the previous one. Transpose. Okay. So while you think about this, some is saying ask about the kernel. Well, just look here. So you can row reduce your matrix to a matrix like this, right? And row equivalent matrices have the same kernel. So you need to find the solution set of the system Bx equals 0, which basically is x equals 0, y equals 0, right? So it is exactly that, not much more than that. Okay, so it's just finding a nice version of the matrix by elementary row operations, for example, and then you solve the system and you find the kernel. So what will be different here? Well, as probably some of you noted, well, I think it would be best to call this matrix B, probably. So we can keep the matrix A from before and save some time, right? So B is the transpose of A. So as some of you noticed during the lecture, yes, the column space of B, so the column space of the transpose of A, is just the row space of A. So I have nothing to do here. And similarly, the row space of B is just the column, is the, well, yes, it is the column space of A, right? Because if you look at the rows of matrix B, they are just the columns of matrix A. So we don't need to compute much about row space and column space. However, about the kernel of B, well, this is different because a matrix and this transpose are not row equivalent. So you need to compute this. You need to solve the system Bx equals 0. And now you see there is something. Since the rank of matrix B is going to be less than 3, It means that there exist, and the system is homogeneous, there exist infinitely many solutions. Right? In other terms, you have only 2 equations and 3 unknowns. It is homogeneous. You will find solutions, and you will find many of them. So the kernel is not going to be the zero space as before. And you find the kernel by row-reducing matrix B and performing the usual operations. Okay, do you have any question or remark? Yes, there exists infinitely to the 1 solutions, because if you look at this matrix here, the rank of B is 2, right? It cannot be 3 because it's 2 by 3, it's not 0, and it is not 1 because the rows are not parallel. So this means that the kernel of B is going to be the linear span of just 1 vector, infinite to the 1. It means the linear span of just, oh, sorry, yes, infinite to the 1, yeah. It's just the linear span of 1 vector. So you can go and find this vector by row reducing the matrix, as we did many, many times, okay? So that's something you can do. Then if you do it now, we can compare your answers. So Jean Herrera has a suggestion. He says 1 minus 2, 1. Well, what you can do to see if it is correct, you multiply, right? And see if it works. So Jean Herrera says, well, to me, this is going to be 1 minus 2, 1. And to see if this is correct, so let's put a question mark here, what you need to do is to take the matrix and just multiply it by the proposed solution. So 1 minus 2, 1. And so what do we got? We got 1 minus 6 plus 5, which is actually 0. And then we got 2 minus 8 plus 6, which is again 0. So yes, it is true. This is a solution. We know it's going to be infinite to the 1. And so we get exactly what we wanted. Okay. If you don't have any remark or further question, we can call it a day. Take maybe this last 5 minutes as a break and then go back to our next commitment. So any other question or remark you'd like to make? Okay, so have a nice day to you too, and see you after the weekend next week, right? Good.